হ্যাঁ ঠিক আছে, একদম ঠিক আছে, এটাই বেস্ট, এটাই বেস্ট।
স্টার্ট করা আছে। Good evening, everyone. So today I will talk you about the spin structure of the proton, as you all know. Yeah, I will talk about the spin structure of proton, as you all know. I hope you have read the abstract I have sent to you. So without delay, so I will talk about the plan of my talk. So what I will discuss first is the basics of particle physics, like in 5 minutes, like just what particles we have, and then we will start our QED processes, and these two are the basic things we will talk about, and then these 4 things like EP scattering, Proton model, EIS and SIDS for the single spin asymmetries, these are the core topics I will discuss, and my work is basically on this last 2 topics, and if time permits I will show some codes like so this will be 1 or 2 minutes long. So what is elementary particle physics? So elementary particle physics addresses the 2 main questions, that what is matter made of at the fundamental level. That is the most important question, that why we are studying the proton structure and so on. And the next thing is how do they interact with one another. So it is very important to study particles, because if they do not interact, we can't study their properties and various things. So we need interaction, and all matter particles interact with each other. So we will talk about that. So these are the main experimental sources from where we get the data, and we study the particles in details. Like first one is scattering events, like 2 particles scatter with each other and produce more particles. These are called scattering events. And then decay process is like 1 particle decays into various particles. So that is decay process, and these are spontaneous processes in many cases. And other one is bound states, that we all know, like proton, that we will study. And for studying bound states we need the upper 2 parts, like scattering events and decay, because if there is no interaction there will be no scattering, and we can't study the bound states. So first thing is like why particle physics is called high energy physics. So it is very simple. We all know that De Broglie relation, lambda is h by p, and lambda is wavelength and b is momentum. So to prop the small length scale, we need small wavelengths, we all know. So if lambda is small, then P is large, and large momentum means high energy. So that's why these two are equivalent things. So these are the units we will take, like particle physics used these units like C and H that they put 1. And the interesting thing is that in this unit system, energy, mass and momentum, these all have same units, and particle physics is generally use electron volts. So this is the standard unit. Then what is the classification of elementary particles? So they are classified in mainly 4 groups. First one is hadrons, then leptons, then intermediate vector bosons and Higgs boson, which is also known as scalar boson. And these hadrons are further classified into baryons and mesons, as you all know. So just briefly I will talk about them. So leptons, there are 12 leptons in total, electron 1 tau and their corresponding neutrinos. So why there are 12? Because there are antiparticles of each of them. So there are 12 leptons and these are all fermions, spin-up particles. Then comes baryons and mesons. Proton and neutron falls under baryons. They are primarily made of 3 quarks, and these are mesons, K1 and so this K plus K minus. So what are their general configuration? So mesons are like QQ bar configuration, like 1 quark and 1 anti-quark. So they are bound states of quark anti-quark pair, and they are generally bosons. So these are important meson particles, pi plus, pi minus, pi zero, that we will study in. I am working in these things. I will talk about that later. And there are baryons, which are QQ configuration, means made of 3 quarks. They are bound states. So proton, neutron, and there are other particles also. So they are all spin half, proton and neutron. So as you all know, the quarks are the elementary constituents of hadrons, and the most important thing is that quarks comes in 3 colors, like red, green and blue. I will not talk details about why they come, because there are historical reasons also how these things come. So if anybody interested, I will talk about it later. So there are 6 quarks you can see, and they are all spin half particles. So why they are spin half, I will talk about it later in part 1 model. There are experimental verifications also. So why they are spin half, and all hadrons should be colorless combination of quarks. So it should be any observable matter is colorless combination of particles. So there are total 36 quarks, like 6 here, 6 are the antiparticles, and then 3 colors. Total 36 quarks are there. So these are the fundamental interactions in nature. So electromagnetic interaction, basically electrons take part in electromagnetic interaction. Strong interaction, they take part, hadrons take part in strong interaction, and there is weak interaction and gravitational interaction. So electromagnetic and gravitational are more general things we see in daily life, but these two are we don't see daily life in daily life. They are predominantly in the nuclear structures. So the theory behind the electromagnetic interaction is QED, and strong interaction in QCD. So I will talk about these 2 things. I don't know much about this electroweak theory or interaction, I don't know. And the interesting thing is that gravitational interaction is not in the standard model. So I will not talk about this also. as we seen the four fundamental forces, and their corresponding particles, they are called mediator or force carriers. So gluons are the mediators of strong force, and there are 8 of them, 8 gluons. And photon is the mediator of electromagnetic force, and there are 1 photon only. And these are Z boson, there are 2 W boson, W plus minus. So there are 3 of them, and they are basically mediators of weak interaction. And there is 1 scalar boson, who is basically responsible for mass in all of the particles. So in brief, standard model includes total 61 elementary particles till now, 12 electrons, 36 quarks, 12 mediators, and 1 scalar boson. Okay. So this actually concludes the basic part. Now I start QED process. So QED in one line, this is like the definition. The QED is basically electrodynamics of spin-up particles. Basically electrons, muons, or leptons basically follow this. So to start in theory, we will start from the Lagrangian or any fundamental theory. So I will not describe this rigorously, I will just explain the Lagrangian. So this part, the first term is like the free part, the free Dirac part. Means this essentially encodes the dynamics of the fermion that we are considering. And if we impose the local U1 gauge symmetry or gauge invariance, we can find this other term also. And this term is the interaction term, and mu, the gauge field, comes naturally out of it. So this is the interaction term, basically the interaction between the gauge field and the fermion. And this term we put by hand. This is the kinetic part of the gauge field. And this is the most important thing, that this gamma mu is the Dirac matrices, and we need this extensively in our calculation. So this is the thing. And from this Lagrangian we can get the equation of motion, that is the Dirac equation. It is written in momentum space. This is the interacting Dirac equation, and it is given as this potential. And any initial and final step we take as free steps, for any interaction. So now comes the most important thing, that is scattering cross section. So basically we have 2 particles. For suppose like A and B, they scatters and produce C and B. Right. So cross section is defined, means intuitively it is like the effective area seen by a target particle, means effective beam area seen by a target particle. But mathematically it is given like this. This is the definition. So the initial flux means the initial beam flux, and WFI is the transition rate per unit space-time volume, and it is multiplied with number of final steps. So this is the more compact way to write the cross-section expression, where you can see this mod m square is called the invariant amplitude. This F is called the flux factor, means the initial beam flux, and this ellipse is called the Lorentz invariant space factor. Means this is the differential. So this mod m square is a dynamical part, means each only depends on the nature of interaction, but these 2 parts does not depend on the nature of interaction. These are dynamical parts. But for A plus B to C plus D process, like if it is a QED process or QCD process, but these will not change. Only this mod m square will change. So basically our all calculation boils down to calculate this mod m square. And this is just the expression for A plus B to C plus D. This is the expression for D ellipse. I will not go in the calculation part, but you can see this delta function. This is a 4-dimensional delta function. Basically, these are 4 momenta. So this actually tells us the 4 momenta is sponsored. And center of mass frame, we can give the definition for the cross section like this. So you can see that it is proportional to modern square. So basically we will calculate modern square. And there is energy, CM prime energy is S. So any questions we will have till this point?
So if the process is different than A plus B to C plus B, derives will change.
Yes, means with the kinetics,
Just like A plus B
kinematics
plus
will
C.
change it, then it will change. But the modern square will change for the interaction.
The derives takes care of momentum conservation and
Yes, it will take care of all. So this is one example, and we need this example. There is electron muon scattering. So this is called the Feynman diagram. There's 2 particles are coming. They are interacting by exchanging a photon, and they comes out. So basically, we want to write the expression for M. So there is a rule. There are some rules. You can write this expression. Those are called Feynman rules. Actually, they come from QFT and from first principle, but you can find a table where all the rules are written. So basically, this part is due to the photon. This comes due to the photon. This is called the propagator, and this part is due to the upper part. And IE down basically the particle factor, and these 2 are the external line factors. Just you need to multiply all of them, and the IE down is this particle factor, and these are the external line factors.
So what's G mu?
G mu is eta mu nu. The D cos theta. And this Q square is the momentum transfer. Means if this is K prime, this K, so that is K prime minus. So we can write, so this expression we can write as this thing, modern square. So basically you can separate out the electronic part and muonic part. So this part is called the electronic tensor, and this is called the muonic tensor. And Q is momentum transfer. So for unpolarized processes, we need to take the spin average and sum over all spin states. So this is one important thing, because unpolarized means we are not detecting the spins or we are not measuring the spin. So we have to take average always. So if we do that, we will find the expressions like this, the electronic and muonic. By this notation, I think familiar is like mu gamma mu is given as S. And so the main thing is, I like to say that the trace calculation of gamma matrices, actually the main thing in cross section calculation. So basically cross section calculation boils down to the trace calculation of gamma matrices. So you can say that, you can see that you need to calculate this trace to calculate the cross section. So how do you calculate the trace? So this is the key relation for gamma matrices. This is the definition, the anti-computation relation, and from this all the trace formulas are derived. You can say the trace of identity matrix is 4, because we are in 4 dimensions, and trace of any odd number of gamma matrices is 0. And these are trace of 2 gamma matrices and trace of 4 gamma matrices. But these are all easy things. But when you calculate the trace for a complex problem, so you need to calculate symbolically in computer. So time part which I will show. In form or mathematical, you can calculate the traces of gamma matrices.
Can you explain what is the gamma matrix? Small.
So gamma matrix comes in the Lagrangian of QED. So I cannot explain because I need to explain the. So gamma matrix is basically I don't know. This is a non-trivial thing. I cannot explain physically. Okay. So after calculating this, you get these relations. In the electron and muon tensor. And from this, if you substitute this and at high energy limit, means neglecting the all masses, you get the mod m square to be this. So here we are introducing three variables, which are Mandelstam variables, and they are also Lorentz variables. So these variables are defined as together Abhirup variables. Here, so I will not explain much. So now, if I am just giving you one example how the calculation is done. So if there is something called crossing symmetry, so you can like change the particles here. So it is electron to mu, and for that thing, the S and P will be switched. So you can see that. So for this thing, if you calculate in CM frame, the STU will be given as this, where theta is the scattering angle. So you can calculate, I think, high energy means neglecting the masses here. Then you will get the unpolarized cross section as this. So these things are experimentally actually measured, and these things are reported from experiments. So we actually match these things from theory. So this is the expression of cross section in CM frame, and alpha is very important thing. Here in QED is the coupling constant of QED, or this is the fine structure constant. So this is the integrated cross section. Integrated means this, you just integrate over the solid angle, whole solid angle. So this is the expression, and it perfectly matches with the experimental results. So QED is successful this year. Everything matches correctly. Now the most important thing, that what will be in lab frame. In lab frame you can calculate this same expression. It will come like this. So the important part is like cos square theta by 2 and sin square theta by 2. The coefficients are important. Just remember for a while. Okay. And E prime and E are the initial and scattered electron energy in lab frame. So from here actually QCD starts. We can go to QCD from this pathway, from QED to QCD. There may be another way, theoretical way, like I have started QED from the Lagrangian. You can start from it, but this is the more phenomenological way or experimentalist way to start QCD. Means we will start from this relation only. This is the key relation, that electron muon scattering cross section in lab frame. So you start QCD from here. So basically you start talking about EP scattering. So EP scattering analysis tells us about the structure of proton. So this analysis will tell us structure, about the structure, how it is an extended object, not an elementary particle. So it is a composite particle. So you see that. And here theory and experiments we get together, because only theory, because there is no theory, this first of all, which predicts the structure of proton. So we need experiment for this. So before going to the QCD part, I will talk about simple experimental evidence that why proton is not an elementary spin-up particle. It comes from the famous experiment, maybe you know G-2 experiment or the magnetic moment experiment. So for any particle, the magnetic moment, spin magnetic moment is defined as this thing. So here G is called the gyromagnetic ratio, and from QED we can prove that theoretically the G is approximately 2 for any Dirac spin-up particle. Okay. It is approximate, not exactly. Now we did the same experiment with proton and neutron. So these are the experimental results for proton and neutron. So it is clearly deviates much higher, it deviates much from the two. So this actually clearly shows that proton and neutron are not spin-up particles like Dirac particles. So these are extended object or composite particles. So this is simple proof. So now we'll go to the theory part. So one note is that we are considering all unpolarized processes, means we are not considering spin till now. So if we suppose proton is a point particle, this is the assumption, then the EP scattering cross section will coincide with the UV scattering cross section. So same expression will be there, only the mass will be proton source, except replacing the muon source. So this is the point scattering cross section. So we are considering proton as a point particle, but experimentally it is found to be wrong at higher energies. So this is not the case. So if proton is an extended object, then we can theoretically calculate that this cross section will come to be this thing. You can see the coefficient now change. The G and GM comes. So these are called the form factors. So basically, this encodes our knowledge gap of the proton structure. So there is a detailed calculation how there are only two form factors, but I will not get into the detailed calculation. So basically, these functions encode the structure of the proton. So basically, we don't have any theory. That's why we don't know what it is. The only way to get this function to feed the data, feed the experimental data. So this is the Feynman diagram, modified Feynman diagram for EP scattering. So proton is now not a point particle; it is an extended object now. So this is the thing. So actually, people have experimentally fitted the data, and they found this functional form of G, which is given as this. And from here we can extract two important information. First one is size of the proton. Actually, if we expand it, take a lot expand it, the coefficient will be some mod of r square. Expectation value of r square. From this, we can get the size of proton. And if we Fourier transform this, we will get the charge density or charge distribution. And we found that this is exponential. So this is actually some important properties of the proton structure. And also, if we Fourier transform GM, that I have not written, we will get the magnetic moment density of the proton. So basically now we want to increase the energy further. So basically these are the chronological order, means the EP scattering is behaving like point scattering when it is very low energy, but after that in some energy it is means higher energy, it is behaving like the elastic scattering. Now if we increase the energy further, then this EP to EP scattering becomes EP to EX scattering. Means the final state means proton is not seen, where a jet of particles, you can say. Means these are all unknown particles. There can be many of them. So this is the modified picture. If we increase the energy further, this scattering is known as the inelastic scattering.
What is the order of magnitude of energy?
I have to check. Sorry. There is experimental data of slab. So I think after 1 G, scattering becomes EP2EX scattering. So what is the cross section expression? So up to this we are writing this LL. Now we have to replace this thing with some another tensor which is called the hadronic tensor. Basically it encodes all information about the hadron vertex. That is an extended vertex. And using some assumption and calculation, use long calculation, you can find this is the most general expression of W mu. So again there are two unknown functions. One is W1 and one is W2. So they basically encodes the whole thing about the proton star.
This hadronic tensor is symmetric, right?
Yes, this is a symmetric hadronic tensor because till now we are considering unpolarized particles. I will come to the anti-symmetric one. Okay. So for inelastic scattering, the cross-section expression becomes this. So you can see again the cos square theta by 2 and sin square theta by 2 coefficients have changed, W2 and W1. So these W2 and W1 are called the structure functions. So there is a difference between the previous expression and this because this is double cross section, right? D prime d sigma. So the before the expression that was only d omega. Only d omega is there. If you differentiate with respect to e prime, one delta function will come. Just keep it in mind because it will be needed. Any questions up to this? So you can make any comment also.
Could you please shift on the previous slide? What does that mean? Extended vertex. Extended vertex.
Oh.
What is
Extended vertex means the proton is not now a point particle, right? It is an extended object, means it has some structure.
What do you mean by vertex?
Vertex means this. It is a terminology in Feynman diagram. These are called vertex. Means the at the moment when the photon interacts with the proton, it's called vertex.
Vertex is where lines meet.
Any questions? Any other questions?
No, I was asking what is capital P? Capital P there in the expression of W.
Oh, capital P is the momentum. Momentum of the proton. Momentum of the proton. And Q is the like momentum transfer. Q. You can write P. Okay. Now we are going to the most important part. This is the Proton model. So basically it is introduced by Feynman in 1969. Maybe most of us don't know actually about this. So partons refers to the constituents of the proton. Parton means the parts of the proton basically. So are these quarks? So these are not quarks, these are quarks and gluons both basically termed as partons. So Proton model is very important as it gives like experimental evidence for three things. First is like proton has 3 valence quarks. The first thing, and gluons are inside the proton. This is the second thing, and quarks are spin-up particles, Dirac particles. Means quarks follow QE. These are the 3 main experimental verification comes from this model.
What do you mean by valence quarks?
Okay, I will explain. So we have seen this expression that now we want to increase the energy further. Okay, just go back to the like EP2EX scattering. Well, in this level, now we want to increase the energy further. Now suddenly the interesting thing happens that the cross section expression suddenly behaving like 0.7. So EP2EX scattering suddenly behaving like EP2EP scattering when we increase like energy very high. So this basically implies very simple thing, that there are some constituents inside the proton which actually interacts with the virtual proton. So these are called the partons. So basically the simple thing, like two cross sections are now equal. The EP to EX scattering is similar to EP to EP. Actually it is EQ to EQ. More fundamentally the mass will change, quark mass. So basically if we now just equate, I think one slide is showing. One slide.
Escape.
Yes. This is the main picture. So basically, virtual photon is interacting with proton. This was the picture. Now we are increasing it further. So basically, the interaction takes between quark and the proton. So we are not just equating the coefficient of cos square theta by 2 and sin square. So a delta function comes because there is a d prime. So from this you can see that W1 and W2 at very high energy basically a function of only one parameter. It is q square by nu, not two variable functions. So this is experimentally actually verified. So they actually depend on the ratio, not on q square or nu separately. So q square is minus q square. Okay. Q square is minus small q square, and nu is the lab frame energy difference. Means E prime minus E in lab frame. So basically, in high energy limit, means q square 1 tends to infinity. So basically, they are replaced by two single variable functions. Basically, so this is called the scaling. This is called the Borkin scaling, and it is confirmed experimentally in slide that they are the single variable functions, W1 and W2. So this is very important. This is called the Borkin scaling. And now the Borkin scaling can be pictured as this thing. So basically, where the virtual photon interacts with photon, you can write this as sum over all the processes where the photon interacts with the quark, and you sum over all the quarks, and here x is the energy fraction, means momentum fraction carried by the parton. So if p is the momentum of the photon, the parton will carry hp. So this is the momentum fraction, and energy will also be c. So from this we basically get the concept of parton distribution function or PDF. Means we can write this as FIX. These are called the PDFs. As PIDX, these are probability distribution, where Pi is the probability that the parton I carries a fraction of proton momentum fraction x. This is called the parton distribution function. I think any questions do you have?
Yeah, so when we say that at high energies, it also becomes an EPD scattering. But we can model it as a sum of all the scattering of between electron and quark, right? So at the end, do we still get electron and proton scattering, or do we not?
Yes. Because we are summing over all the contributions. Right? Any questions? Any other questions?
This one would be preference. So that means when we are summing it, it does not remain a proton, right? We are just saying it is a proton because it is scattered over.
Yeah, we are seeing the total cross section.
Yeah.
So basically, those are fundamentally another process, not the electron proton scattering.
Yeah.
Electron quark scattering.
Thanks.
Okay. Now the PDFs should satisfy the following property. By just multiply both sides with P, you will understand. This xp is the momentum of the parton. So we are integrating with the probability distribution. So we will get the total momentum. And these are the kinematics of proton and parton. So if proton's energy is E, parton will be xc, momentum will be xpl, and this is the longitudinal momentum. And most important thing, we are not considering the transfer momentum here. We will consider it. So this is the old parton model. This is very old, it's 1969. So here PT is 0, it is 0. So basically W1 and W2 replaced by the single variable functions. So we can express this in terms of the PDF. And these F1x and F2x are also related. And this relation is called the Callan-Ross relation. So basically this relation is possible because we are considered quarks with spin-up particles from the beginning, and this relation is experimentally verified. So this actually gives the proof that quarks are spin-up particles. So if quarks are not spin-up, this expression will be changed, some other expression. And this is experimentally verified. This is called the Callan-Ross relation. Okay. Now we will go to the experimental verification that why proton has 3 valence quarks. So basically, proton is a dynamical system, not like 3 quarks are there only. So 3 are valence quarks, and 3 quarks will always be there. They UUD, and these are called valence quarks. And there can be many gluons, and there are C quarks. C quarks means any quark antiquark pair. So it spontaneously generates quark antiquark pair. Means a gluon can emit quark antiquark pair. So this is a dynamical system. So basically there are 3 valence quarks, gluons and C quarks. So it is not a simple system. Basically we can actually calculate.
Are the colors of the valence quarks in the proton is random or they follow some pattern?
Yes, and they will follow. They should be colorless.
Colorless quarks is it?
No, means the combination should be colorless.
Oh, means they cancel out.
Yes.
One blue, one green, and one blue. Like
Yeah, something like that.
The C quarks can be measured as C quarks?
Yeah, we can calculate the contribution of them, like from the PDF. Yeah, I will come to that. So basically, we can calculate the structure functions. Here it too. The calculation is not so hard. We can get these things. So basically, UV is the PDF corresponding to the U quark, U valence quark, and dV of X is the PDF corresponding to the D valence D quark, and S is the C quark contribution, C quark PDF. And this is called EP scattering, and for EM scattering in neutron we can calculate the similar thing, but neutron has one U and 2D, so that's 4 will be there and will be same experiment. So now you can basically see that when x tends to 0 and x tends to 1, these are 2 extreme cases, the ratio will be only 1 and 1/4, and from this we can like have a theoretical plot that how F2ENX by F2EPX looks like versus x. This is the plot, and this plot is experimentally verified. So basically this is experimentally verified by SLAB, and this actually shows that Proton model is correct, and proton and neutron has 3 valence. So this is the second proof. Now what about gluons? So basically gluons are not charged particles, so that's why they are not probed by virtual photon. That's why they are not captured in the PDFs. So I have shown you the relation that this should follow, right? The summation of x fi x. If we sum over all quarks, it should be 1. But they have found that contribution of all quarks is not 1. So basically it is less than 1. So let's introduce the factor epsilon g. So which is the momentum fraction carried by the atoms. And it is found from experiment that this is like 50%. So 50% of the momentum of the proton carried by the gluons. This is the experimental justification. Gluons are also there. So any question?
Is epsilon g cannot be predicted?
No, because gluons are not electrically charged, so they are not interacting with the particle proton. You will not. Yes, sir. Okay. So this is the most important part. So this is DIS and SIDS process. I also don't know much about it because I am working in it. So deep university scattering is basically the same process that I have discussed, that EP2EX. N means any electron, electron means the scattered electron. It is the same process. EP2EX means EP2EX. So what is deep mean? Deep mean that it is very large. Q is very large compared to the lambda QCD. So there is a parameter in QCD after which the perturbation theory works. It is called the lambda QCD factor. And inelastic means the final state is not the same at now. The unknown states are there. And this is also called inclusive process. So this is GIS process. Do you know?
Your microphone is not working.
They want to- Why it is why it is okay? So now we'll talk about SIDIs. So SIDIs is semi-inclusive deterministic scattering. So previous one is inclusive. Now it is semi-inclusive. Semi-inclusive means we are detecting a particular hadron in the final state. Means we are detecting a particular hadron. It can be pion or something else. So process is similar like DIS, where we are now detecting a specific final state hadron. Okay. So basically these are pions or pions. Okay. So basically this is a complex process. As you know, it is not A plus B to C plus D, one extra particle act. So this SIDI basically gives access to something known as transverse momentum dependent pattern distribution functions. So till now we have considered transfer momentum of pattern to be 0, but now we will see the effect of this. And also give access to the fragmentation functions. So fragmentation functions also are probability distributions. So this actually has interpretation that a quark Q to hadronize into hadron H. So what is the probability distribution of that? So these are called fragmentation functions. So basically SIDS allows us to study these effects like Kahn Sierra effect, Sisberg's effect. I will not talk about this today, and these are the things that I am working on. This is single spin asymmetries and being single spin asymmetries, and there are many other asymmetries also, the spin orbital correlations. So these are the coordinates we use, basically light from coordinates. So any 4 vector written as this A plus A minus A part, where A plus minus is defined as this thing, and A part is a two vector A1. So basically this is the transverse part. So we are separating out. And this is the temporal part, and this is the beam direction, basically A3. So we are taking this as A plus minus. And this is the picture of SIDIS. So you can see that the electron comes and scatters, and it interacts with the proton, with the virtual photon, and the hadron H comes out. So basically the transverse momentum and the momentum defines a plane which is known as the hadron plane, and this plane is known as the electron plane, and this is the spin of the proton, and there are some angles, phi each, phi, this comes in the calculation. So this is a standard picture of SIDIS, and these are the variable, kinematical variable here. So these are confusing, like similar type expressions. So there is another confusion terms, like now we talk about spins, actually spin cross sections. So basically spin polarization and helicity, there are similar kind of things actually that comes. So spin actually corresponds to the intrinsic angular momentum of a single particle. But polarization is something like the corrective spin of the beam. So if longitudinally polarized means the beam is polarizing the parallel to the beam's momentum, and transversely polarized means polarization of the beam is perpendicular to the beam's momentum. And helicity is given as projection of spin along the direction. I have just keep this slide because there is a confusion and I become confused. So this is the unpolarized GIS. So till now we are not considering polarization, so all spins are averaged. So this is the expression of the cross section using the pattern model. So you can see that PDFs comes into play here. So these are the collinear PDFs, means no KT dependency there, means no transformation dependent, and X and Y are the two Lorentz invariant variables. This is called the Borkin variable. This is something called inelasticity. So these are useful variables, so that's why we are expressing the cross section expression in terms of dx dy in this fashion. So for unpolarized SIDIS, the expression becomes complicated because the transfer momentum actually plays a role here. You can see now this FQ is a PDF, but it is a TMD PDF. So it depends on the KT also. And DHQ is basically the fragmentation function. It gives a probability. It has a probability interpretation that the probability that the quad Q hadronize into hadron H. So this is the probability interpretation of this, and Z is defined as this. Which is A is the hadron. Okay, any question of this? Any questions? You can calculate that X and Z are basically these things, K plus by P plus. Basically this is the longitudinal momentum fraction of quark, and Z is the momentum fraction of the hadron. And I have said that if Q and TH are the TMD PDF, and this is the fragmentation function. So now we come to the polarized spins, means we are now considering the spin of the initial and final states. So we have seen the electronic and hadron tensors are symmetric for unpolarized states. Means when I have talked about the unpolarized GIS, then the hadron tensor and electron tensor was symmetric. But now the antisymmetric part comes into play. And this is the antisymmetric hadron tensor, and you can see there are again two unknown functions G1 and G. So these are called the structure functions again, and these are called polarized structure functions. So basically for polarized GIS there are 4 structure functions, like 2 previous one, F1, F2, and these are G1 and G2. So basically this is the more mathematical expression to express W mu for GIS process, like this. So we are taking the trace of an interesting quantity here. You can see this is phi is called the correlator or quad correlator, which is expressed as this expression. So I'll come to this in a while. Basically we can integrate it and write it as a single variable function fx. So you know Taylor expansion, like you can expand any function, but there is something another kind of expansion which is called the twist expansion, and we can expand this in twist to mean. Twist to means the leading twist. The leading term is of twist to, and it can be expanded like this. This is a leading order term, you can say. So here 3 functions comes here. Fx, this is the normal period that we have talked about. Fx is the normal period, and G1 and H1 comes for the, as we have considered the spins of the final states and initial states. So G1 basically, and they have the same probability interpretation, like F is the unpolarized period, G1 is the longitudinal period or velocity, and H1 is the transverse. Now for polarized SIDIS, the expression becomes more complicated. As you can see, there are total 18 structure functions for polarized SIDIS. Polarized means we are considering spins now. So you can see that there are FU, cos phi. There are many functions are there. We are not going to details. So for SIDS process, you can again express the W mean, that hadron tensor, like this. Again a trace of 2 quantities now. One is phi and there is delta. So phi already was there in GIS. It's the quad correlator, and delta is the fragmentation correlator. So now for GIS we can expand the correlator. For SIDS also we can expand it in the leading twist, in the twist expansion, and it gives 8 bit distribution functions. Like this is F1, there are 8 of them, you can see, and this chart actually gives the probability interpretation also. So F1 is basically to the probability distribution of finding unpolarized quark inside an unpolarized proton. Similarly, H1 part is the finding transversely polarized quark inside an unpolarized proton. Similarly, like all of this. And these are the 2 important functions, that is F1 P part and H1 part. F1 P part is called the Sieverts function, and H1 part is called the Bohr-Molder function. So actually Sieverts rate comes from this. So I will not discuss about this. So any questions?
So the probability of finding so that is T stands for
Transverse, transverse.
so the and so the probability of finding a transverse curve inside a transverse nucleus has 2 distribution functions.
Yes.
What is the significance of that?
Yeah, I don't know. In the mathematical expression, there are 2 such distribution functions are there. Like you can see, there are 2 blank places also.
Yeah.
Means theoretically, it is not possible to find longitudinally polarized quark in an unpolarized proton. I don't know basically what mathematics tells us. These are not possible. Okay, now, so any other questions? So, this is the last part. This is a single spin asymmetries. So So we are considering beam and target both are polarized till now. Now, what is your intuition tells if we switch the spin of the target particle? Is the cross section become same or will different? It will be different. So it is experimentally found that the cross section actually changes. If the target spin is changed, the cross section is also changed. So it is non-trivial thing, and it is explained that this is called the asymmetry. Single spin asymmetry is defined as this thing. So basically, the numerator is the difference between the cross section when the target spin is up and when the target spin is down, and the denominator is the unpolarized part, the unpolarized cross section. Now, experimentalists measured the asymmetry with some modulation also. I don't know the exact reason. So they actually means the same thing, just integrating with eyes and things like that. So this is the SSA with a modulation. So basically different experiments like Hermes, it is in Daisy, Germany. Class, it is in JLab, USA. And IACS is a future experiment will also be operating in the next decade maybe. So they basically report the SSA for different SIDS processes. They basically experimentally report these SSS for different SIDS processes. Now, for the job of a high phenomenologist is to explain those observed SSS theoretically. So we have to explain these SSS theoretically, or we have theoretically predict the SSS for certain experiment which will be carried on in the future. So for some future experiment we can predict theoretically what will be the SSS. So this is the sector I am working in. So I am going to give an example of some specific SIDS experiment where the beam is longitudinally polarized and the target is unpolarized. And this is the cross-section expression. So you can see that there are two structure functions, not 18. Only two are important now. It's FU and FLU sin phi. So these are the structure functions for this specific experiment. And these are the expression of this FU and FLU, which come from theory. And the most important part in the FLU, this part is same. We have seen it previously also. This F1D1. This part is now interesting that this EQ term is the twist 3 and the second order term you can say. After that we are considering only leading order terms. So this is not a leading order term. It is a twist 3 term, twist 3 distribution, and here is D part Q, which is also a twist 3 distribution, and the rest like D1, H1, there are twist 2 distribution. So basically these are twist 3 PDFs, TMD PDFs, and D1 is a twist 2 FX, and these are fragmentation functions. So the corresponding SSA is called the beam single spin SSA, the beam single spin asymmetry BSSA, and this is given as this thing, this expression as a function of PT. So you can see the big expression like you have to replace FLU and FU with that expressions. Basically these are all 6-dimensional integrations to perform in numerator and denominator. With time permits I will show the code for this. Basically, what is the problem? So let's go back to the correlator expansion. So this is the correlator expansion. So main problem is lies in this. This is the proton state. So the main problem is the proton state. Proton is a dynamical dynamical object. We don't know what its state because it is not a fundamental particle. If it is a fundamental particle, we know exactly what will be the state. Like for electron, we know from Dirac equation and like that. But for proton, there is no such equation which can determine the state. So this is still unknown part. So we need some model. essentially to model the proton. So the model comes here. So proton is a composite particle. The state of proton is not known. So we need some models. So there I have written two models here. First one is quark diquark model. So basically we are considered proton is made out of two quarks, means two particles. One is quark and one is diquark, means means there are three quarks. So we are taking one quark to quark and the other two quark to a single particle, which we call diquark. This is the simplest model, I guess. So this is also a spectator model, and this is also an abelian theory. So this is a simple theory. So and there is something called quark target model, where we consider the proton to be only a single quark. These are simple models. So basically, using these models, we can calculate the TMG periods. Like we can calculate the correlator and then the periods. And these are some parameterization as well. So this is an example. Like the asymmetry is plotted here using the quark diquark model, and this is from the class experiment. So these black dots are the experimental data, and these red and blue lines are the calculated plot. So you can see that models are not like always works. So you can see in this region this model is works perfectly. In this model it fails. So this is the model by Mao and Lu, 2013. So now comes the main thing, the title of my talk, that the proton spin crisis. We know that proton is made of three quarks from the knife quark model, the basic thing. But we have seen that quark is not, proton is not made of only quark, there are gluons and C quarks also. So this is a dynamical system. So basically, like EMC collaboration first measured the proton's polarized structure function, that G1 and G2 I am talking about. So basically, from this we can calculate the quark spin contribution to the proton spin, which is this term, and from intuition these terms should not be there, and this delta sigma term should be 1. Means all the spin contribution should come from the quark. But this is not the case here, and there are some contribution to the proton spin from the gluons, from the angular momentum of quark and gluons also. So this is known as the proton spin crisis. So whether the proton spin actually comes from as well as quark, as well as gluons, and the orbital momentum of orbital angular momentum of quark and gluons. So any questions in this? So I have said that this delta sigma is a spin contribution of quarks to the proton spin, and this is measured from the that SSS or TMD is involved in the polarized DIS or SIDS. But I don't know the calculation behind this, how to get this delta sigma, proton spin contribution. And this delta G means the gluon contribution you can find through another experiments like polarized PP collision and DIS. And H2 energy, I don't know about this. These are obtained from some lattice fluidity techniques. You can calculate this. So proton spin puzzle is still an open issue because there are some issue with these calculations because these are not exact. So the issues are that the collinear periods that we have talked about, those are universal. So this means these are process independent. I mean, if you calculate the PDFs for one process, you can use it for another process. So this is a very useful thing. That's why PDFs are available in libraries, in Python library or like Fortran, you can find those. But the problem with TMD PDFs is that these are not universal and they depend process to process, and that's why you have to calculate again and again what are the TMD PDFs. And and these things also vary with the scale, vary with the energy. But for collinear PDF, the evolution equation is known from QED, QCD. The how, if we change the energy, how the PDFs will change. But for TMD PDFs, we don't know the exact evolution equation. So these are the open questions. So what is the evolution equation for TMD PDFs? And there are other issues like calculation of TMDs within a model, like I have said that quark target model or quark diquark model. So this is a perturbative process, means calculation of TMDs within a model. But fitting the parameter from the experiment, because when we calculate the TMD period within a model, there are some free parameters we have to fix, and we need the experimental data here. That process is a non-perturbative process. So this is a mixture of two things that is not good things, I believe. These are the open issues. And future aspects is like there are many high energy experiments like EIC. There maybe we get some more result from this, and we can get the consistent TMD evolution equations that will make solve the proton spin crisis in future. So that's it. If you have any questions.
It's a very technical topic.
I know, I have written
this.
this.
People like me who did that for many years. So I would like to ask you that on this talk, I would like to take some key takeaways that what is the actual problem you are going to address. And you showed that you are showing some models and there are some things you are relating with some experimental evidence, right? So I would like to ask you that why you are doing that. Is the actual problem that is not known till now that you are going to address with a model which is already being proposed and the experimental evidence?
Yes.
Just for a short synopsis that we can have some takeaway from this. Can you do that?
Okay. So basically the problem is this thing. The problem is the proton spin crisis. Basically. So what is that? So from the naive quark model means the first quark model means when the Gell-Mann proposed it. So when what do you think? What is intuition said that total spin up proton is a spin up particle. So the contribution comes from the quarks. So that should be 100% contribution. If we sum the spins of the quarks, we will get the spin of the proton. But that is not the case. It is found in experiment that the gluons and the orbital momentum of the quark and gluon also contributes to the spin up particle. So this is not one. This delta sigma is the spin contribution of quarks to the proton spin. So actually the problem is now what is the percentage of this thing? We need to know exactly, right?
And that you have calculated that the single spin asymmetry will be equal to d sigma.
Yes.
How you relate that thing with this calculation?
Okay. That I don't know exactly how actually this thing calculated using that TMDs or SSS. But those are like probes to this calculation. So those used in these things to calculate delta sigma. And there are many things because this is only a sector to calculate this thing. So this thing is calculated through any other experiments like PP collision and this thing like lattice Q series. So these are like various branches are there. So this is one of them.
This class is quite known to me because I'm doing nearly same thing for electron spin. You say that you are putting a target and putting some beams like that, both are polarized. I mean, doing same thing, some material with the ferromagnets and the electron spin polarized kind of thing. So this same calculation I followed, and so I was more interested to know what you actually want to prove with this thing. I mean, why it goes like that. Very nice.
So any other questions? Or any comment? You can say anything.
Well, I would like to mention one thing. As you said in QED that the basic fundamental symmetry is local gauge symmetry, but technically speaking, local gauge symmetry isn't observable in QED. Like every symmetry should have a Noether chart, and that Noether chart for QED transfer to electric chart, which comes from the global gauge symmetry. Local gauge symmetry gives rise to certain charges which are not observable.
I have written because the interaction comes from them.
Yes, exactly. The photon field cannot come without the
Yeah.
local gauge symmetry. But technically speaking, in lab you will never be able to observe the local gauge symmetry of QED.
Yeah, that maybe. I don't know because I have not done any formal study of this QED. I just like this is my pathway to learn the things I have presented. I don't know, this is a broad subject, I know, so it will take more years, maybe.
And it was a very technical talk, but it was followable, so that's a big applause to you.
So, can you show the course? So before showing the course, I will talk about something, some collaboration that she is my mentor, Professor Anurada Mishra, and I am working under her. And they are the postdoc students there, and she is my project partner. So we are basically working in QTM model right now. So we are converting the E and G part distribution in QTM model basically, and we'll do the same calculation like SSI or beam SSI. So these are the references, like these are the 3 books that I have read. The first one is Swavel, and this is the most important book, that Halden and Martin, personal reference. I am, this book is like Bible of this particle physics. And these are some of the papers, and these are the lecture notes of Bacheta, and this is a PhD thesis of my postdoctorate Dada. Thank you. So আমি ওটা শো করবো, তাহলে এখানে ওটা অন করা যাবে?
Oh, আচ্ছা। Yeah, I guess.
Oh, sorry. So I will show my course.
ওখান থেকে প্রেজেন্ট করে ঠিক আছে আচ্ছা
অনলাইনে কেউ নেই তো?
you have to post in your have the post yes.
Switch off right now. Time তো তোর হটস্পটটা দে বা কিছু একটা কর
আমি দিচ্ছি
হটস্পটটা
চলে আসে
ঠিক আছে অন হয়েছে মিটিং থেকেও তো বেরিয়ে গেছে
না দিয়েছি আচ্ছা কাজ করতে
হ্যাঁ একটু দা
I can display it from here.
কি আরে হয়ে গেছে তো কোড রান করবে না করতে কিরকম ক্যালকুলেশন হবে দেখা হচ্ছে প্লটটা আমি জেনারেটরটা দেখা হচ্ছে আচ্ছা এখানে কি এই জয়েন হয়ে যাবে জানি না প্লট তো মনে কতক্ষণ 5 মিনিট 5 মিনিট লাগবে আচ্ছা স্ক্রিনটা ওটা ফুল স্ক্রিন করে নে ওখানে না না ওখান থেকে ফুল স্ক্রিন কর এটাকে না আমার কি হয়নি
I hope everyone can read what is on the screen.
প্রবলেম হচ্ছে কি এখানে মাঝে মাঝে দেবে নি প্রবলেম
Can you guys see the screen? Like, is this your blocking the view or something?
So, as I have mentioned, the asymmetry expression. Remember the asymmetry expression. Okay, one second. So this is the asymmetry expression. You can see that A sin phi is LE. So we need to calculate, and we have to substitute this FLU and FUU expression. These are the expressions. So these are the FUU and FLU expressions. So we have to substitute it here in ALU expression. So basically the numerator and denominator becomes 6 dimensional integration. So we have to do this. So this is the code. I think you can read. Yeah. The first one is like importing the standard libraries, and there are some Proton modules also. You can see that PKHFF. So basically we are importing the fragmentation function from a Proton module. So basically these are some constants and kinematical bounds we have done, and these are the definitions. Will that Q square, like the gamma and epsilon, whatever is there. So these are the expressions for the SIDS, and this is the model that I have used, the quark diquark model I have set. So these are the model expressions. I have not actually included in slide basically. So all these are model expressions. These are basically simple things like functions in Python, just defining the functions. This is the FU and FLU. So this is the FU function. You can see I have written here, and here I have imported the fragmentation function basically from the Proton module, and I have used for the basically I have used for pi 0, means pi 0. We are detecting the pi 0. So for pi 0 we are importing the fragmentation functions here. So similarly the FLU expression is also similar. You can see that basically this is the numerator integration. Basically this numerator and denominator I have taken separately. So this is the integral numerator and this is the integral denominator. I am not explaining. And then you have to integrate. There is a library called Vegas. I don't know, library or the Python module which can integrate, like multi-dimensional integration you can do very easily. So this is 6-dimensional integration. I think 2-dimensional integration I have done by hand. So this is a 4th dimension. You can see there are 4 bounds. And then you just save the data and plot. So basically I am running this code right now and generate this plot. Most probably this plot. I'm showing this. So in this slide you can see this plot, right? I have included this plot. So basically I am generating this plot maybe, if I am not wrong. This plot. Let's see. So just wait for some time. So it will started integrating. Backwards. So there will be, you can see how many integrations. So for numerator it will be 10 iteration, and in each iteration it will do 5,000 integration. So basically 50,000 integrations, and the denominator also 50,000. For I think x values, 30 x values we have got. So this is the plot. You can compare it. Black color. So this is the generated plot. You can see this plot, the fourth one corner, the blue plot I have reproduced. So this is the same thing. And these black dots are experimental data. So this is the coding example. Any questions you will have?
Does anyone have any questions, comments, suggestions? Guys, let's thank the speaker once more. Shweta?